Hello everyone, good morning, good afternoon, and good evening wherever you are in the world. Welcome to my channel. In today's video, we will walk through another sample problem regarding on the design of beam shear reinforcement part 1. So on this example, we are covering two main topics. The first one is a quick design concept explaining how the shear reinforcement formula is derived. The second one is the theoretical spacing of shear reinforcing bars or stirrups as the factor design shear force increases. So let's dive into the problem, and here it is. The beam shown in figure below was selected using the yield strength of 60,000 psi and the shear strength of concrete 3,000 psi using the normal weight concrete. So we are required to determine the theoretical spacing of the stirrups using number 3 bars for each of the following shear. So we are given from A to D. From A, we have the maximum shear force of 12,000 pounds up to 150,000 pounds. So we have the cross section here of the beam. This is the profile of this number 3 ties, and we have the effective depth of 24 inches. The width of the beam is 14 inches. So first of all, we need to discuss regarding how the formula of the spacing is derived. And we have the elevation, the representation of the diagonal cracks, and we have the vertical representation of the stirrups. The spacing of stirrup is, and we have the distance D. If this is 45 degrees, as per the ECI code, then this is also D. So the nominal shear strength of the stirrups is Vs is equal to EV times Fy times N. So EV is the area of the ties crossing on the beam sections. That is times the Fy, and N is the number of stirrups crossing on the beam section within the distance D. That's why the number of stirrups within the distance D is equal to N is equal to D over S. That is if we calculate the number of stirrups crossing within the distance D. So the next one is the one of the provision of the ECI code, equation 22.5.10.1, that the maximum shear force should be less than or equal to the design nominal strength of concrete, where the nominal shear strength of concrete is equal to composed of design strength of shear strength of concrete plus the design strength of reinforcing steel. P here is equal to 0.75. Then the next one is Vs. That is the shear strength of the shear force of the reinforcing steel, which is equal to EV times Fy times D over S. So if we substitute this into this formula, we will have this one here, where EV, this one, that is the area of the stirrups, is equal to the number of legs times the area of the ties. So if you notice, if we use the U stirrups, that is equal to 2 legs. So we have to multiply this by 2. If we are using the closed stirrups, still 2 legs, whether it is closed or not, still 2 legs, because we are considering these vertical legs, that is 2 also. But in the real practice, in the site, we are using the closed stirrups. I have not used this so far. They use stirrups in the field. Then if we use this 2 set of ties, we have the 4 legs, 1, 2, 3, 4. So if we use the flat beam, normally we have these 3 ties, let's say 3 ties or 4 ties. It doesn't matter even if the width of the beam is wider compared to the depth. still is counted as 3 ties. You have to count the ties here, 3. This beam is we call it a plot beam, concealed beam. This is very common practice in the Middle Eastern countries like Saudi Arabia. Then the next one is to determine to calculate the VS. VS is equal to VU minus the design strength of concrete all over the P value, 0.75. So the spacing of the stirrups is equal to EB times FY times D over S. So S, if we determine the value of BS, then we can calculate the spacing of the ties. So that is the how the spacing of ties calculated, derived. And now this is the representation of the general arrangement of the stirrups with beam shear reinforcement. We have the spacing of stirrups actually, but in our problem we are giving the BU, the distance D from the face of the support. So we are calculating the spacing of these ties within the distance D. So this is only the representation of how the ties and the main reinforcement is arranged in its general elevation. So let's get started with the solution. So from E, we are given 12,000 pounds. Using the normal weight concrete, lambda is considered as 1. So the design shear strength of concrete is equal to P times 2 times lambda times the square root of FC prime times the cross-sectional area of the beam. So we have 0.75 times 2 times 1 times to the square root of 3,000 strength of concrete times the cross-sectional area, 14 times 24 is equal to 27,605 pounds. And that is according to the ECI table 22.5, 0.5, and 0.1. This is you will find the formula in that table, this one here. So the stirrups are not required if the VU is less than half of the design shear strength of the concrete. That is according to the ECI code 9.5.3.1. And that is one of the provisions. So if we calculate the half of the design shear strength of the concrete, that is equal to 27,605 divided by 2. That would give us 13,803 pounds, which is greater than 12,000 pounds. So meaning stirrups are not required. That is according to this code. Now in letter B, we increase the design maximum shear force to 40,000 pounds. The stirrups needed here, because the BU is greater than half of the design shear strength of the concrete. So by inspection, we have already calculated this 1/2 of the design shear strength of the concrete, which is 13,803 pounds. So therefore, the theoretical spacing of the stirrups need to be calculated. So VU is equal to PB sub C plus design strength of the reinforcing steel, which is BS. If we calculate the BS, that is we have VU minus PBC all over P, that is 40,000 minus 27,605 pounds all over 0.75, and that would give us 16,527 pounds. So the spacing of the ties is equal to based on this formula, 2 times 0.11 square inch. So take note, guys, that the 2 here is represent the 2 legs of the beam in our example. If we are using 3 ties, then you have to put here 3. So 2 times 0.11, this is the area of the ties, now using number 3. Times 60,000 psi times 24 inches. This is the depth of the beam, all over the value of BS, which is 16,527, and that would give us the actual spacing of stirrups of 19.17 inches, which means that is the required spacing of the ties within the distance D from the face of the support. So the next one is to find the maximum spacing to provide minimum area according to the ACI code, that is 9.6.33. So the spacing from this formula is equal to EB times the yield strength over 0.75 times the square root of the strength of the concrete times the width of the beam. So that is equal to 2 times 0.11 times 60,000 psi over 0.75 times the square root of 3,000 times 14 inches. That would give us 22.95. So the other provision is spacing equal to EB times Fy over 50 times the width of the beam, which is equal to 2 times 0.11 times 60,000 psi over 50 times 14 inches is equal to 18.86. So these are the minimum minimum spacing of the ties according to these code requirements or provisions. So the next one is to compute the maximum spacing of the ties. So D over 2 less than or equal to 24 inches. So we have to calculate this if the BS is less than or equal to the square root of F sub C prime times the cross-sectional area of the beam according to this code here. So BS is equal to 16,527 pounds less than to 4 times the square root of 3,000 times 14 inches times 24. That would give us 73,614 pounds. So if you notice here, the value of BS is less than to this requirement. So therefore, we need to calculate that spacing equal to D over 2, which is 12 inches. And this is that controls of our spacing, which means if you space this 12 inches according to this calculation using this equation here, if you space the stirrups all throughout the span 12 inches, that would be okay. So the next one is the shear force. We are given 60,000 pounds and we are required to determine the spacing of the stirrups. So the theoretical spacing of stirrups here, you need to calculate first the BS. So BS is equal to BU minus the shear strength of the concrete all over P. That is 60,000 pounds minus 27,605 pounds over 0.75 is equal to 43,193 pounds. So that is the value of shear force, shear reinforcement of the steel. So the spacing is equal to EB Fy times D over BS. So if we multiply this 2 times the 0.11, the area of the ties, times the 60,000 psi times 24 inches over 43,193 pounds, which is this one, That would give us the 7.33 inches. So this spacing, guys, is the required spacing from the face of the support to the distance D. So that is the spacing 7.33. The next one is to determine the maximum spacing to provide minimum EB according to this code here, 9.6.33. So that spacing, according to this formula, we have the EB times the Fy over the 0.75 square root of Fc prime times B width of the beam. That would give us 2 times 0.11 times 60,000 psi over 0.75 times the square root of 3,000 psi times the width of the beam, 14 inches, is equal to 22.95 inches. So we still have another provision for the spacing of the stirrups, which is EB times Fy over 50 times width of the beam. So 2 times 0.11 times 60,000 psi over 50 times 14 inches, that would give us 18.86 inches. That is the spacing of the ties based on this code requirement, the maximum minimum EB. So the next one is to determine BS, to check whether it is less than or equal to this one. So but here 43,193 pounds less than to 4 times the square root of 3,000 times 14 times 24 inches is equal to 73,614 pounds. So which is less than. So therefore the maximum spacing is D over 2 is equal to 12 inches. So the next one is the last one is the maximum. We are given the maximum design shear force of 150 pounds. So here Vs is equal to Vu minus design shear strength of concrete over P, that is equal to 150,000 pounds minus 27,605 pounds divided by 0.75. That would give us 163,193 pounds. So by inspection, Vs is greater than 8 times the square root of Fc prime times cross-sectional area of the beam according to this code 22.5.1.2. So if that would be the case, 163 is greater than 8 times square root of 3,000 psi times 14 inches times 24, which is 147,228 pounds. So therefore the beam is insufficient, so we need to increase the size of the beam, or maybe we increase the value of the concrete. So that's all, guys, for this video. And if you find this video helpful and if you learn something about this about our topic, please don't forget to like, subscribe, and if you have any question, please comment. So thank you very much. See you next time. Bye bye.